Hey, it's Jeff Hansen again. I hope you enjoyed part one of this, which was due on Monday, where I really tried to define how to number both linear and cyclic forms of glucose. And now I want to build upon that and use what you've already learned to go to a slightly higher level of complexity. If you're still doing this on Monday, that's great, but it's just as well to do it on Wednesday. I want to remind you from Monday that this is a simple nucleophilic attack of O5 on carbon 1, the aldehyde group, in order to cyclize glucose either into the alpha and beta forms, and that the little bitty hydrogen is the only axial atom that's pointing straight up or straight down. It won't tend to bump into glucose as much as if it were the hydroxyl group. Which of these forms do you think will be most prevalent in blood? The alpha glucose or the beta glucose? And by the way, you'll notice the D. Can you remind why I put alpha D glucose and beta D glucose? It's the stereochemistry of the chiral carbon atom, which is furthest from the anomeric. So it's at the far end. The very last carbon is not chiral because it has two hydrogen atoms, but the number 5 carbon is chiral. Hence, and it does have D stereochemistry, hence beta D or alpha D. Not a major point since most biologically relevant sugars are D forms. I would like you to look at alpha and beta glucose and tell me which of these you think will be most prevalent in human blood. Please pause the video and answer the question now. However, I'm moving on. The question about which is more prevalent really means which has a higher and lower energy. The lower energy something is, the more prevalent it'll be. The higher the energy of something is, the less of it will form. So what's the difference in energy between these two molecules? The only difference structurally between these two molecules is the stereochemistry at the anomeric carbon. One hydroxyl points up, the other points down. Now, low energy generally means being more spread out in space. When you have large atoms like oxygen and carbon, the more trans bonds there are, that's the more often the backbone reverses, up, down, up, down, up, down, the lower the energy. Anytime there's a cis bond where you go up, down, down, there's a cis bond, those large atoms are crowded together and it is going to occur less often. So which of these is all trans? Is one of them cis? Please take a look and see. Let's start with beta D glucose. First we'll look at the atoms on the top of the cycle, starting with the hydroxyl. Up, down, up, down, up. Every bond is trans. Let's look at the bottom of the cycle. Up, down, up, down, up. Every hydroxyl group in beta D glucose is equatorial. Now you can look and say, hey, what about this oxygen on carbon 6? Well, you realize that's not directly linked to the ring. Rather, there's a linking carbon group, so this hydroxyl is free to rotate. The linking carbon, carbon 6, is equatorial, as are all the hydroxyls. In contrast with alpha glucose, let's do the same trace starting at the top of the ring. Up, down, down. Let's look at the bottom of the ring. Up, down, down. The hydroxyl coming off the anomeric carbon in alpha glucose is cis. It tends to bump into this ring more than the equatorial oxygen on the anomeric carbon of beta glucose. And in fact, let me emphasize that by just pointing in red a tracing showing everything is trans going across the top of beta glucose, whereas there's the one cis bond in alpha glucose. We can also look at the bottom trail. It's always the same. A cis bond is going to be higher in energy, and as a result, in your blood right now, about 2/3 of the glucose molecules is in a beta glucose, a cyclic form. About 1/3 is in alpha glucose cyclic form, and less than 1% is linear. This is kind of fortuitous. This aldehyde group is very reactive, and as you age, that aldehyde is going to interact more and more with more tissue in your body. Or if you have diabetes and have extra linear glucose, it'll interfere with things. It's nice that over 99% of your glucose, that reactive aldehyde has interacted intramolecularly and is now inert, held into the cycle, which can float around and bring nutrition throughout your blood at very little expense. This nomenclature that I've been using, where I refer to hydroxyls as equatorial or axial, is really important because you do not need to memorize a single Fisher diagram if you have a conformational figure. You can absolutely identify glucose based on stereochemistry in a conformational figure based on applying a single algorithm. You want all of the hydroxyl groups to be equatorial. You want all of the heavy atoms linked through trans bonds, with one exception. And what's that? Please answer. The one hydroxyl which does not have to be equatorial is the hydroxyl linked to the anomeric carbon, because that can point either up or down. It's anomeric. It doesn't have a specific stereochemistry. In a conformational figure, glucose makes perfect sense. Glucose has the lowest conformational energy of any hexose, because every single hydroxyl in it is equatorial, pointing away from the mass of the ring, and only these small hydrogen atoms are pointing axially, straight up and down. They can bump into the ring, but they're so small they don't contribute much to energy. And in fact, this equatorial versus axial nomenclature is so important. Let me go ahead and throw the earth up here. If you have any question about it, please do contact me. Applying your current understanding of glucose to these figures, will you identify which of these sugars is glucose? Please go ahead. At this point, I believe you should find this question trivial. You simply apply the one algorithm that glucose is going to have the lowest possible conformational energy. All of its large atoms should be in trans bonds. All of the hydroxyls should be pointed equatorially away from the central ring. So let's look at the first example. We can see, let's see, is equatorial, which is this, which is this. These are all equatorial. Wait a minute. What about this hydroxyl? Do you see how it's pointing vertically straight up? This is an axial hydroxyl. It's not the anomeric carbon at the opposite side, at the right hand of the figure where it should be. So in fact, absolutely not glucose. How about this one? Equatorial, equatorial, equatorial. Never worry about carbon 6. Oh, hey, this is an axial hydroxyl. Is this glucose or not? Ed, I hope nobody's tricked by that. This is the anomeric carbon. It's linked to two different oxygen atoms. It is axial, but that's allowed. Which form is this, alpha or beta? Let's see. The hydroxyl is below the plane, swimming like a fish. It's an alpha. How about this one? Well, right away you probably noticed we have an axial hydroxyl on carbon 2. This is not glucose. How about this one? Equatorial, equatorial, equatorial. Everything's equatorial. This is the lowest possible conformational energy. Not only is it glucose, which form of glucose is it? The beta form. And to confirm that, here we have the hydroxyl above the plane of the glucose, flying like a bird for beta. Now, I do want to go one step further. This is a slightly lower priority learning objective, but can you identify the first sugar in this figure? Please take a stab at that. Well, we said it wasn't glucose, and we see that what carbon number has the axial hydroxyl group? Well, in the case of glucose, the anomeric carbon is carbon 1, 2, 3, 4. So carbon 4, you'll notice, is on the complete opposite side of the ring as the anomeric carbon. And it turns out that the monosaccharide galactose is identical to glucose except at carbon 4, where its hydroxyl has the opposite configuration, which would put it in this axial position. And we will talk a lot about the dimer lactose, lact from lactation or milk. Lactose is the sugar in milk. And when you break the dimer apart, you get glucose and galactose from lactose. And I just want to point out that the central sugars I've talked about, galactose, glucose, fructose, and glycerol, each of these enters central metabolism through a different entry point. So I've spent a lot of time talking about monosaccharides and disaccharides, glucose, fructose, sucrose, high fructose corn syrup, galactose, glycerol. And now I want to go and describe in more detail polymeric forms of carbohydrates. In order to do that, I would like you to begin by trying to write a short definition for each of these terms related to carbohydrate nomenclature. You probably have a good feeling for the fact that carbohydrate is the encompassing category that includes sugar, starches, cellulose, which are compounds containing carbon, hydrogen, and oxygen in a ratio of approximately 1 to 2 to 1. Hence the formula CnH2ON. Sugars are a subcategory of carbohydrate referring to small molecules, monosaccharides and disaccharides that are small enough to bind to taste receptors and often taste sweet. Starches, in contrast to sugars, are huge molecules, way too big to bind to taste receptors so they don't taste sweet. They are polymers of specifically glucose. And we'll talk shortly how those glucose molecules are linked in 1,4 alpha-glycosidic bonds, and there are occasional branch points through 1,6 alpha-glycosidic bonds. And again, this is half of all dietary energy. Cellulose, like starch, is a huge polymer of glucose. Starch or cellulose can have 10,000 glucose residues in it. Unlike starch, however, cellulose is linked through 1,4 beta-glycosidic links, and it is the difference between alpha and beta that gives them that very different characteristic that cellulose is indigestible. And we're going to describe why shortly. But accordingly, cellulose is a very common form of dietary fiber. Let's take a look at these polymers. I mentioned that the glucose residues in starches are alpha glucose, and the glucose residues in cellulose are beta glucose. Let's start with the lower figure here. Can you determine whether this is alpha or beta? And can you look at each glycosidic link and tell me which carbon atoms are in that bond? Please go ahead and do that. But I'm going to move on. Now, if you had trouble, we'll zoom in on one of the links. Go ahead and characterize that. Identify the number of each carbon in the glycosidic link and determine whether each glucose residue is in the alpha or beta configuration. So, number one, let's look at the bond. The oxygen atom is here, so the two carbon atoms are bonded adjacent on each side. Can you tell which of these carbons is going to be anomeric? Please do so. Yeah, well, the anomeric carbon has a bond to two different oxygen atoms. And of course, it helps that one of those is always going to be the ring oxygen. So that kind of helps identify it. Also, it follows the rule that the anomeric carbon should be on the right in a figure if that's easy to do. So yeah, the anomeric carbon is here. So what number is the carbon on this residue? Well, the anomeric carbon in glucose is carbon 1, so this is 1. Can you tell me whether the bond is alpha or beta? Well, the oxygen is below the plane of the sugar. That makes it an alpha like a fish. What's the other carbon atom? Can you number it? We'll have to look at this residue to do that. Find the anomeric carbon. 1, 2, 3, 4. So this is a 1,4 alpha glycosidic link. Now can you similarly identify this link? Please do that. But I'm going to move on. So again, We have the oxygen in the middle, a carbon atom on each side. Which of the carbon atoms in the glycosidic link is the anomeric one? Which of the carbon atoms is linked to two oxygen atoms? Yes, it's also on the right-hand side of the monomer, as it is in standard notation. And it's linked to the ring oxygen, so anomeric is here. In glucose, that's carbon number 1. On the other side, we look at the other monomer, the anomeric carbon. Oh, now notice there's an oxygen here, so we'll have to go on the top of it this time. 1, 2, 3, 4. So this is a 1,4 beta link. So the 1,4 beta link makes cellulose. The 1,4 alpha link makes starch. And in fact, it is the nature of these bonds that allow cellulose to form extremely straight structures because every bond can be trans. Up, down, up, down, up, down, up, down, up, down, up, down. You keep reversing the backbone, you can do a very straight line. However, in starch, since every glucose monomer is in an alpha configuration, that means that there is one cis bond for every single glucose residue, which means that this is kinked at every glycosidic bond. It cannot form a straight chain, and generally it forms a curve, as shown here. Now, I'm going to go a step beyond here. What I've described so far is the most important, but I do want to go up one more level in complexity to be sure you understand this alpha, beta, fish, bird nomenclature, because you'll notice that the definition that in beta glucose the oxygen is above the plane of the ring, and in alpha glucose the oxygen is below the level of the ring, then that definition applies specifically to the standard orientation of a conformational figure of glucose, where the anomeric carbon is to the right, where the ring oxygen is above and going back into the plane. What happens then if we take the glucose monomer and flip it over such that each glucose residue in cellulose flips 180 degree relative to the previous? And that is the actual structure of cellulose because these residues will rotate into the lowest energy conformation. In this case, as we would expect, you see that the standard representation of glucose puts the oxygen above the plane of the ring. And by definition, if you rotate that ring 180 degrees, now the oxygen will be below the level of the ring. But you'll notice that in both cases, the oxygen in beta are in the equatorial position. And of course, in alpha glucose, the oxygen not only will be below the ring in the standard orientation, but in any orientation, it will be axial. So maybe we could say that alpha glucose looks like a fish, and alpha is also axial. So that's a slightly added level of complexity to the alpha-beta nomenclature. But why is it then that a straight polymer of glucose can't be digested, whereas a curved one can? These straight polymers of glucose can pack tightly together because they're so straight. It's real easy to pack things together if they're straight. If they're bent or if they're curved, you cannot uniformly pack them together this way. And therefore cellulose packs extremely tightly and extremely densely, and it's one of the most important structural components in nature. In fact, glucose is the most prevalent organic molecule on the planet in a polymer as cellulose, which means specifically that the cellulose form of glucose is the most prevalent molecule on the planet. In what type of role might these really straight, tightly packed fibers form? How about trees? Most of the vegetation you see around you is supported by a lot of cellulose fibers. In contrast to cellulose, starch, with its 1,4-alpha glycosidic links, has a kink for each glucose residue. It cannot form a straight line. Instead, it tends to loosely form into these helical structures, which are very floppy but can pack together, and they are therefore not useful structurally whatsoever. However, because they're so floppy and so highly hydrated with water, they're very accessible to enzymes, and this makes starches with its 1,4-alpha links extremely useful as a fuel. Enzymes can rapidly act upon it and build it up as a fuel storage, and enzymes can readily access it and tear it apart to mobilize it when energy is needed. And what I'm showing here is the simplest form of starch called amylose. Amylose, the simplest starch, is formed from linking glucose monomers through 1,4-alpha links to make one simple linear molecule. In contrast, the more complicated amylopectin is formed by taking these amylose helices and linking them together to make branch points through alpha-1,6 glycosidic links. In fact, typically there are multiple branch points in amylopectin such that there can be 10,000 glucose residues in one amylopectin starch molecule. Accordingly, amylose and amylopectin are the primary storage forms for glucose in plants. Animals, in contrast, store glycogen, which is also made out of alpha-1,4 links with alpha-1,6 branch points. So what's the difference between glycogen and amylopectin? It shows in the figure here. Take a stab at it. This is not real important. Glycogen, it turns out, has a lot more branch points than amylopectin, so that each branch tends to be shorter in glycogen than in amylopectin. The key is that amylopectin and glycogen are very similar structurally and play very similar roles in plants and in animals. That's as far as I want to go. A couple questions here if you want to review some of what we've looked at. I hope you've enjoyed this. Thank you.